Not sure how far we're going to go today. So we're going to be moving forward today, but I think that even in the process of moving forward, it's kind of a small move, but I think you'll find it beneficial for what you're testing on anyway, as far as regarding using the complex numbers. So we're going to start there, and we're going to add what we already know about complex numbers, and we're going to see how this goes. I don't have it planned out like I usually do, so you'll have to bear with me. Here it goes. So let's do this. We're going to call, this is actually section 2.2. And I don't know, you probably, there's an official title. I'm going to call it the more complex numbers. More complex. We'll call it more complex problems. No, I like numbers. It's not really that there's more of them, it's just it's just an understanding. So, let's start with this. We're going to begin, and I want to solve y double prime plus y equals 0. And you may know the solution already, but I want to. It's more of the process that I want to develop. So what we're going to do is we're going to try. Notice that it equals 0. So what solution are we finding? Right, finding a null solution. And when I say try, what that means is we're not going to be using the fundamental theorem of calculus. We're going to be using a method of undetermined coefficients. So our null solution here is going to just be a scalar times whatever solution we find out. It's not necessarily going to be y of 0. Okay? And this question keeps coming up over and over and over. So when you're not using the fundamental theorem of calculus to find your answer, you're going to always need to go back and substitute in your initial conditions. Okay? Do you want me to make that note?
Yes.
That's a good note. I think that's been driving some of you absolutely crazy. And understandably so. So let's make this note. I'll do it this way. We're going to try yn as e, and I'm going to use s, e to the st. I'm using that because there's no a, and because it's a second order differential equation. And note, so here's our big note, and I'll try to paraphrase what we just put, or say more specifically. Note, when you're using undetermined coefficients, using undetermined coefficients, the solution is of the form y null equals some constant, C1 e to the st. And then I'm going to put as opposed to yn equals y of 0 e to the at, which is automatically found put it that way, automatically. You don't have to think about it. Automatically found we're using the fundamental theorem of calculus. The fundamental theorem. That is a long one. My shoulders keep tired right now. Theorem of calculus. So we're not, that's a lot to write. So if we need to refer to that again, we're just going to call it FTC. And if you remember, there's two applications of the fundamental theorem of calculus. We're talking about the integrating one. I guess. Yes.
So since let's see that's because null solution is a family of solutions, right?
Correct.
And so we don't have to put a sigma, but we could put like say a D over an A. And
Sure. Put whatever you want there.
what makes the problem like easier.
Yeah. Yeah. For example, in the logistic equation, there's a factoring in the e to the at term, and it comes out into two places. So if you factor that and then combine your coefficients, it has a y, it has an initial condition plus, I think, like a q over a or something, or b over a in it. Yeah, so that would become, and then they refer to that specific combination of constants as b. Good. And yeah, Hans?
Does this also happen with the
Yes, you'd put a c on there. But then remember, then the c is after the fact. You have, for example, if you integrate t dt, you would write some t what? Oh, whoops. 1, you have t plus some c. Notice it's after the fact. It's not being multiplied by it. That's how they differ. And also, this is kind of an oversimplification if I'm referencing this problem. Why is that? It's because this is a second order differential equation. And I'm going to remind you, and you're going to see it again. But what happens is you need to take a second derivative. When you take the first derivative, you bring down an s. When you take a second derivative, you get an s squared into it. So it turns this into, you're solving a second order polynomial. So there's two solutions. So if this is referring to this solution, then there's going to be two solutions. And we found that, we saw this the other day, that you can add those two null solutions, you get a constant divided by 2, but that's just a constant. So we said for a second order, I'll write that, second order, we end up with a null solution yn C1. And really we have two s's, so S1t plus C2 e the S2t. And we're going to see that in a moment. Yeah.
Is that one null EDA or ESP?
Well, that was when we were referencing, we were using this only for first order differential equations. And they were always of the form, this is solves y prime equals a y. Yeah, a y. All right, let's try this. So we said we're going to try y null right here is y null is e to the s t. So we're going to make a substitution. We need a second derivative, so that means we need a first derivative. That's s e to the s t, and and there's more, and y double prime for the null solution is going to be s squared e s t. Substitute. I'm going to write that, we're going to substitute and solve. Substitute and solve. So that's going to, oh, whoops, this is y double. So this gives me s squared e s t. What do I have over there? Plus e the s t equals 0 or s squared plus 1 times e to the s t equals 0. Okay, we're landing going into the world of complex numbers now. So I think it's careful. I think you want to just be a little bit more aware. We mentioned this last time, I'll remind you, is what we really liked to do at the beginning of class when we were in the natural numbers, or the real numbers rather. Real numbers is we wanted to just divide off the e to the st. And you can, for that, if these are just real values, but it could be a complex value function, so it could have other 0 values. So really what we're doing is, there could be a time when that is 0, but what we also want is this one is this going to give us 0. So we're looking for solutions for s squared plus 1. So really what you're doing is you're saying either this is 0 or this is 0. And we're just working with finding s. S squared plus 1 is 0. S equals, what does it equal? Plus or minus, right? Plus or minus I. Yeah?
Do we get the C's later or?
Right now. Right. Okay, so now we can write our solution. Let's write our solution. So our solution is y null is C1 E I T plus C2 E minus I. So let's try this. How about this? Well, let's see what happens when y of 0 is 0 and y, I'll just show you one. And y prime of 0 equals 1. So you've got two initial conditions. So now we can go back and figure out what the C1 and the C2 are. So let's try that. So first off, we have y of 0. Y of 0 equals 0. This equals C1 plus C2. In other words, I put the 0, that 0 into there, that 0 there, C1, and you could expand those out using Euler's identity to get C. But that, we've got two constants to find, so now we need to use our second initial condition. So let's do that. We're going to take y null prime. Y null prime is going to be I C1 E EIT plus, nope, minus C2 E minus IT. Now we use our initial condition, so that's that y prime of 0 is 1. The EITs, those become 1, so I'm left with I C1 minus, oops, I C2. Notice there should have been an I here. Those. Y prime. You could solve this probably a number of different ways. Really kind of up to you. How about if we say this? This would tell us that C1 is minus C2. Depends about it. And so if we use that down here, we're going to have 1 equals I. C1 is minus C2 minus C2 minus I C2. Did I make a mistake? Is this okay? So 1 is minus 2I C2. And you can solve that. I'll bring it up here. And you can get C2 equals minus 1 over 2I. So C1 equals 1 over 2I. We can write our null solution as 1 over 2I E I T minus 1 over 2I E minus I T. That's how we use the undetermined coefficients and how we start working in the complex part. And probably after the test in our next class, we'll be looking at how that graphs some of, well, we're going to see some of those graphing today. So notice this. Did I make a mistake?
Can I ask you a question?
Sure.
Wouldn't the one
I just gave you the set.
okay, so
I
it's just, okay, so
those could change based on those two. So
We won't get from those conditions, but
you just leave it. That's the best you can do. This is Tom chose those.
so you wouldn't want to solve for y0. You just
Did 1 or 2? Chosen.
I like to choose.
Yeah, that's kind of what I feel like I'm doing. There we go. Yeah. So in actually one of your homework problems, you're going to get to play around different, different initial conditions and see different solutions.
So we wouldn't want to solve it generally. We just would, we won't give an initial condition of y0 and y prime on 0. We just want to leave it in the constant the coefficients of C1, C2.
If you're not given initial conditions, then this is as far as you can go. Yeah. So without initial conditions, that's it. With initial conditions, then you want to go through this process. All right. Let's try. Notice this.